Today we're going to be continuing our practice with the law of sines, and today we're going to be looking at the SSA case. But before that, because there's not much I want you guys to do with the SSA case today other than just kind of determine the number of triangles, I'm going to also throw in this area of any triangle when you're given SAS, so when you're given side angle side. So, and we'll come back to this later in this unit, but still. All right, so the area of a triangle for side angle side. The area of any triangle is given by 1/2 the product of the lengths of the two sides times the sine of their included angle. This right here, the lengths of the two sides and the sine of the included angle implies that we have that side angle side. So what we're going to do is we're going to do, if we look at this, this is saying that we're going to take 1/2, because it's always 1/2 the product, of B times C. So let's just look at what those are. We have B times C times the sine of angle A. Do you see how angle A is between B and C? You could also do the same thing here. If we looked at A and C, notice that angle B is between those. And if we looked at this next part, if we looked at A and B, C is between those. So in that case, what we can see is that basically this formula that we're going to be using, again, is just going to be 1/2 the side times another side times the sine of the included angle. Like, that's really your area formula for side angle side. That's really it. Okay, so I don't want you to think about this being 3 different formulas for you to learn. No, it's one formula. Just as long as you have two sides and an included angle, you just take the side times the sine of the included angle times 1/2. All right, so example A, you're setting up a triangular flower garden in your backyard. Fun. If you lay off lengths of 15 feet and 11 feet for two sides of the garden with a 62-degree angle between those sides, convenient, what will the area of the garden be? So when we think about it, we've got a side of 15, a side of 11, and a 62-degree angle between. So this is enough information for us to use this area formula, that our area is going to be 1/2 times the side times the other side times the sine of the included angle. Okay? So let's just put that in. One of our sides was 15. One of our sides was 11. And our included angle here is 62 degrees. And we legit just multiply. That's kind of nice. So we're going to take 1/2, so you can use 0.5 if you want, times 15 times 11 times the sine of 62, and we press enter, and that tells us that we're going to have, we'll go to the nearest tenth again, so that'll be about 72.8. Now, when we have area, we want to square the units, right? And so this was in feet. So technically we multiplied feet by feet. So we have square feet as our unit. All right. All right, let's try one more. Oh, you guys try this one. Okay. So notice this says a piece of land is bordered by 3 roads as shown. Notice you have a side, another side, and you have an included angle. So see if you can use this formula in this first you try. Go ahead. Okay, so here's what I had. Again, this fit the side angle side information that we had. So I just took one side times the other side times the sine of the included angle, and then multiplied by a half or divide by 2. Either one of those is fine. And I ended up getting that the area is about 1.6 square miles. When we think about our knowledge of the unit circle, do you remember when we found area before, we had to do 1/2 base times the height? Well, the base and the height always had to meet at a right angle. And so the right angle would be the sine of 90. So when you think about it, it's kind of exciting. Like if you think about taking like 1/2 the base times the height times the sine of 90 degrees. Now we don't remember that from the formula of an area of the triangle, do we? Well, that's because what is the sine of 90 degrees? Oh, it's 1. So really, we've been using this formula all along. It's just that we had to have a base and height that were meeting at a right angle in order to use that. So I don't know, I just think that that's an exciting connection to the unit circle values that we've studied before. Okay, well, let's move on, because one of our goals is going to be to solve any type of triangle, regardless of the information that we know about it. And remember that when we are given non-right triangles, we can't use right triangle trig to solve. So we can't use like opposite over hypotenuse for sine, because there is no hypotenuse in a non-right triangle. So we discussed in the previous lesson that we can use the law of sines when you're given 2 angles and a side, so the AAS or ASA case, or 2 sides and an angle opposite one of those sides, the SSA case. I know we haven't learned it yet, but we can also use the law of cosines, which is another law that we'll be learning in this unit, when you're given 3 sides, side, 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 or 2 sides and the included angle, kind of like we were dealing with in the other triangle. And now in these problems, we're not talking about finding the area, we're talking about like solving, finding all the missing side and lengths and angle measures. Well, all we're going to do for now is this A and B part. We're going to identify the information given. If we have angle, angle, side, side, angle, side, side, angle, side, 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 or side, angle, side. And then if law of sines can be used to solve the triangle, we'll write law of sines. And if it can't be used, it'll be law of cosines. So we're kind of like getting ready for things in the future. It's really kind of a nice, just like take a deep breath and organize our thoughts lesson, okay? So in example 1, let's take a look at what we have. We have a side marked, another side, and an angle. But what do you notice about that angle? Do you see that the angle is between the 2 sides that we have? That means that this is a side angle side triangle. And if it's a side angle side triangle, that means that it's not going to fit, that it's not going to fit in the law of sines. And if we think about it, do you see that we don't have a side to put over that the sine of this angle? So we can't use the law of sines, so we're stuck using the law of cosines. All right? Number 2. Let's look at this. Again, I have 2 sides and an angle. This time though, do you notice that the angle is not between the 2 sides? That means that this is a side-side angle case. And in a side-side angle case, that's something where we can use the law of sines. And if we look, we have an angle and a side opposite that angle that we could use to set up that original ratio. So this is going to be the law of sines. Okay? Let's look at 3. This time I have 2 angles and a side. So I have an angle, another angle, and a side. Notice the side isn't between the 2 angles. The side is outside those 2 angles. So that's going to be considered angle, angle, side. And if we look, we can see that we have a side and an angle opposite that side. That is enough information for us to set up the law of sines. Okay. Number 4, we have 2 sides and an angle. What is this one going to be? Well, I see that this angle is not between the 2 sides, so that's going to be a side-side angle case, SSA. And we do have enough information to set up the law of sines. So we're good. Number 5, we have a side-side-side case. We don't have to worry about the order there. They're all sides. And we don't have any angles to help us set up a ratio. So that's a big clue that we can't use the law of sines. So that means that we'd eventually use this law of cosines. Okay. What about this one here? Did you say side-side angle? Very good. And hopefully you see that we have something where we could set up a ratio to help us with that law of sines. Oops. 3 more. Number 7. Side-side angle. And this one is the law of sines. This is angle, angle, then a side. Whoops. So AAS. And look, I do have something I could set up the law of sines here as well. And then another side-side angle, and that's another law of sines. Okay, so that's the first part. Okay, now caution has to be exercised when using the law of sines in this SSA case, okay, because you don't want to spell it backwards. Depending on the relationship between the 2 sides and the angle, there could be no triangle, 1 triangle, or 2 triangles that are possible. And that's what we're really going to look at today, is how many triangles would be possible in these SSA cases. So we're not going to go forward and solve those triangles. We're just going to really differentiate to see how many triangles we would get. Okay. Now, one option is that our angle is obtuse that they give us. Okay. So let's say that the angle is obtuse to begin with. One thing we should have learned in geometry is that when you have, like in a triangle, the largest angle and the longest side are across from each other. So if I have an obtuse angle, then the longest side should be across from that angle. All right. So we're just going to make sure that the side opposite is bigger than the other side given. Okay. Well, if the side opposite the obtuse angle is smaller than the other side, that doesn't make any sense. So that means there is no triangle. But if the side opposite the obtuse angle is larger than the other side, then there is 1 triangle. Okay. So if the angle is obtuse, then we just double check. We make sure that the side opposite that obtuse angle is bigger than the other side that's given. Just kind of use our knowledge that way. Okay. Now, if the angle is acute, we have to be super careful. One thing that might happen if the angle is acute, we'll set up our ratio for the law of sines, and in the calculator, we'll get a domain error. Guess how many triangles that means? That's right, folks. That means that there is no triangle. Those are my favorite because it's pretty obvious, like there's an error, and if you believe you set everything up right, then that tells you that there's no triangle. Okay? But let's say that we don't get a domain error. if we're able to get a value, we need to remember that when we use the inverse sign in our calculator, that the inverse sign only gives us angles that are in quadrants 1 and 4, if we're in degrees from negative 90 degrees to 90 degrees. So obviously in a triangle, we're not going to get angles that are negative, okay? But isn't it possible that an angle in the triangle is obtuse? And that means that somehow we need to find angles over here. Remember that sine is positive in quadrant 1 and quadrant 2. So the angle theta that we get is going to be one of the answers for sure, okay? But we also have to check if the supplement of theta, which is our quadrant 2 angle, can be used to form a triangle with. So essentially what's happening here is that we have this other, let me use this here. We have this, like the theta prime that's here, and we're looking at this specific angle. This angle could also be one of the answers. The calculator can't give us that, remember, because the calculator is only going to give us things in quadrant 1 and 4. So we have to find the quadrant 2 angle and see if that is a possibility, okay? Now, when we think about our idea of reference angles, what we can do for that is we'll always take 180 degrees minus the theta value that was given, okay? And that's going to be our quadrant 2 angle. Okay, so our quadrant 2 angle is found by 180 degrees minus theta. Okay, so now how do we know if that, and again, this is an obtuse angle, that's totally possible in a triangle. So how do we know if that obtuse angle could be part of our triangle? Well, what we'll do is that we're going to take our found quadrant 2 angle and then add the given angle. So like the original given angle, like in the problem, not the given angle from the calculator, but the angle given in the problem. As long as those two are less than 180 degrees, then we can make a second triangle, okay? So let's look back, and that's all we're doing today is just trying to decide how many triangles are possible, okay? So let's look back at those examples that we just did, and let's determine how many triangles are possible. Now, the good thing is that we only have to like be cautious when it's an SSA case. The other cases are all one triangle, regardless, okay? This SSA case is where we might have to turn back here and take a look at our rules, okay? So let's look back at example 1. This was an SAS case. And the SAS case means that we don't have to worry about it, that this is just one triangle, okay? Do you want to go through and mark all the one triangle cases? That sounds good. All right. So this is an SSA that we're going to have to be careful here. AAS, that's safe. That's one triangle. SSA, we got to be cautious. SSS, we're good there. That's one triangle. SSA, got to be careful there too. SSA, okay, got to be careful here. AAS, we're good. And then SSA, we got to be careful, okay? So we're going to have to practice our rules, but now at least we've marked all the ones with one triangle in them. So let's try example 2. Since this is an SSA triangle, let's think about these rules that we just discussed and see what the rules are. Remember, if the angle's obtuse, we just need to make sense of the situation. If it's acute, let's set it up and go to town, okay? And what we see in example 2 is that the angle is acute. And since the angle is acute, that means that we should set up our work for the law of sines, okay? So let's set up that work. And remember that we can take the opposite, the side and the angle opposite each other and form a ratio. So we're going to take 30 over the sine of 57 degrees. And then the other side we have is 32 over the sine of whatever angle this is. Do you want to call it A? We'll just do that. Here. There we go. There's angle A. Okay. So angle A. And based on what we looked at, what we can do is we can cross multiply. And we know that the sine of angle A is going to be 32 times the sine of 57 degrees over 30. And because we're trying to find angle A, what did we have to do? That's right, we had to take the inverse. So let's take the inverse sine of 32 times the sine of 57. Oh, oops, not yet. All over 30. Now I can close the parentheses. Okay. And that gives me 63.5 degrees if I'm rounding to the nearest tenth. So what I see is that the measure of angle A could be 63.5 degrees. Okay. I didn't get a domain error. So what that means is that I need to double check here. Let's find my quadrant 2 angle. Because remember, when I used inverse sine, my calculator is only giving me quadrant 1. So let's find this quadrant 2 angle to see what that's going to be. So the quadrant 2 angle would be 180 minus 63.5. So my quadrant 2 angle would be, oh, sorry, can you see this? Would be 116.5 degrees, okay? Now, is it possible that I could take this 116.5 degrees and this 57 degrees and have room for another angle of the triangle? Well, let's see. So 116.5 plus 57 gives me a total of 173.5. So is there room for a third angle of the triangle? There is, okay? So this 116.5, our quadrant 2 angle, plus our 57 degrees, our original angle, was less than 180 degrees. And so when it's less than 180 degrees, that means that a second triangle can be formed. And therefore, this is a case that has 2 triangles. Okay? Well, let's look at example 4, since we said example 3 was just 1 triangle. So example 4 is an SSA case. And let's look at the angle. Oh, it's an obtuse angle. So if we have an obtuse angle, we just make sure that the side opposite is bigger than the other side given. If it is, there's 1 triangle, we're good. So I look, and the side is 25, that's opposite the obtuse angle. That's bigger than 18, right? So here, I'm just writing for our little notes that we have an obtuse angle and that the side opposite is bigger. So that means that this also has 1 triangle that's possible. Okay. We said example 5 had 1 triangle. Example 6 was SSA though, so we should set this up. So what we could do is we could take, here's our ratio that we can set up, 2.8 over the sine of 50 degrees equals 4 over the sine of whatever this is. I'm going to be really creative and call it A again. Okay. All right. So we can cross multiply. We get that the sine of A would be 4 times the sine of 50 over 2.8. Now, to find angle A, we want to get rid of the sine, so we'd have to find the inverse sine, right? So let's take the inverse sine of 4 times the sine of 50 over 2.8. Uh-oh, we got a domain error. That's probably the best news we can get. Because when we get a domain error, what that means is that there is no triangle that is possible. So because we got a domain error, we can stop and we can say that there is no triangle. And again, that was because of the domain error that we got. Okay. Let's try these next ones. Example 7, we have to go back to, because this was a side-side angle case. I look, it's not an obtuse angle. So that means I've got to set it up. So I've got 32 over the sine of 52 degrees equals 42 over the sine, again, I'll call that of A. Okay, so we have that the sine of A is going to be 42 times the sine of 52 degrees over 32. And so to find that, what we would want to do is take the inverse sine of this. So we would take the inverse sine of 42 times the sine, times the sine of 52, my goodness, over 32. Oh, and I get a domain error again. And so because I have this domain error, that's nice. That means I just have one triangle. Okay. Last one here. We have an SSA case again. So it's acute, so I'll set up 85 over the sine of 70. Remember that opposite side and that opposite angle in a ratio with each other. And then I have 88. And then again, I'll just call this angle A. So using cross multiplication, I would take 88 times the sine of 70 degrees over 85. And let's see, again, I'd have to find the inverse sine of that. No such luck. We have a measure of an angle. We have the measure of angle A, and that's going to be about 76.6 degrees. So because the angle was acute and it was an SSA case, what we have to do is we have to find our quadrant 2 angle. Remember our quadrant 2 angle, we're going to take 180 minus this 76.6. And that gives us 103.4 degrees. Okay. Again, the calculator gives us this acute angle, but this is also a possibility. So let's see what we're going to get here. Let's see if we take this quadrant 2 angle and this original angle, if there's room for a third triangle. Okay, so let's try it. Let's take the 103.4 degrees plus the 70 degrees. Again, this is the quadrant 2 angle we found plus the original given angle. And you probably don't even have to add it together to see that this is less than 180 degrees. And because it's less than 180 degrees, that means that there are 2 triangles that are possible. Okay, so you might say, well, when would a triangle not be possible? Let's just pretend that this original angle was 78 degrees. If we had put 103.4 plus 78 degrees, that's too big, right? There isn't room for another angle in the triangle. So that would mean that that doesn't work and there's just one triangle, okay? So now that we've done a few together, let's look back and try to do this with this type of question. Let's sketch triangle ABC. And again, it doesn't have to be to scale. So here's my ABC with angle A is 40 degrees. Side A is 13 and side B is 16. I can see that this is a side-side angle case, so I'm going to have to test it. All right, so I'm going to take 13 over the sine of 40 degrees equals 16 over the sine. Okay, look, notice it's not A anymore. We have the sine of B. Okay, so I have that the sine of B would be 16 times the sine of 40 degrees over 13. So I would need to take the inverse sine of 16 times the sine of 40 divided by 13. And that gives me that the measure of angle B is about 52.3 degrees. Okay? So now let's look at the quadrant 2 angle B. That would be 180 minus 52.3. So that would give me 127.7 degrees. Could I put, now this is definitely going to be a possibility, okay? But could I also make a triangle with this angle B and 40 degrees? And I see that 127.7 plus 40 degrees is less than 180 degrees. So I'm going to say that there are 2 triangles possible. And it says why. And we could say since we can form a triangle with the calculator angle and the given angle and with the quadrant 2 angle and the given angle. Okay, so 2 triangles possible there. Okay. Lastly, let's do number 11. Again, here's my ABC. You can see they look pretty much the same. It's really just to have an idea of where the sides and angles are. So this says that side A is 5, side B is 12. And I can see that this is an SSA case. So I need to test it. I can't just look at it and say there's one triangle, okay? So I would say that 5 over the sine of 36 degrees equals 12 over the sine of B. So then I see that the sine of B would be 12 times the sine of 36 degrees over 5. And so I could try to do this. So the inverse sine of 12 times the sine of 36 over 5 is a domain error. And we kind of like domain errors here because what does that mean? That there are 0 triangles, okay? So here we can say that there are 0 triangles because I'll say 0 triangles possible since we got a domain error. When trying to use the law of sines. Okay. I know we're at the end. 2 quick things before we go. First of all, when we have a domain error, I don't know why I wrote 1 triangle. This should be no triangles. Okay, everyone get that? Number 7 is no triangles. Okay, I'll write it again. Sorry, I don't know what's happening. All right, and then I want to give you just one last little bonus example of an obtuse angle. Let's say that we had an obtuse angle. Sorry. Okay, let's say that we have an obtuse angle, like just like we did over here where we have 104 degrees, but let's say that this is 18 and this is 25. Okay, let's say we have something like this. Here's an obtuse angle. Do you see that we have an obtuse angle, but the side opposite is smaller? That's a no-no. Okay, that can't happen. So this would be another case of a no triangle. Okay, and there are other cases that could happen, but today we're just trying to get you used to those type of ideas, okay? That's it. So today's lesson, again, just practice the area and how many triangles are possible with the different cases. Have a great day.